Hi, my name is John Krockmalny, and I've developed these visual tutorials to accompany any technical training format that might be delivered. In this presentation, we'll explore networked electrical circuits and how they differ from other types of electrical circuits. In this presentation, there will be three learning outcomes. Number one, describe network circuit designs. Number two, calculate network circuit properties. And then number three, simplify network circuits. As we may already know, electrical circuits have three components: the source of the power, the load that converts one form of energy to another, and then the conductors that connect the source of the power to the load. Typical networked circuits have more than three loads, as shown on this graphic. Notice that the resistors are serving as the circuit loads. Looking further in this graphic, we see that these resistors installed in both parallel and series patterns. Networked circuits are commonly used in electronic devices, computers, and other digital technologies. These networked circuits are using the placement of loads and other electronic components in both series and parallel patterns. Utilizing such patterns in electronic circuits serves to condition both voltages and amperages utilized by the networked circuits. I will use this graphic in this presentation covering networked circuits. Identified is a 9-volt direct current battery shown at the top of the drawing. Notice that resistor R1 is in parallel to the R5 resistor. The resistor R3 and R6 are also in parallel on the other side. Both of these parallel circuits are in series with resistors R2 and R4. Simplifying this networked circuit, we can determine that with the 9 volts DC being applied, the amperage going through the circuit will measure 0.003 amps. Also shown, if a multimeter is configured to read resistance and it's measured across the circuit without the source of the power being applied, the multimeter will display a total resistance of 3K ohms, or 3,000 ohms of resistance. Although the process may appear complicated, it's very simple once the networked circuit simplification steps are identified and carried out. We can start with the parallel circuit made up of the R1 and R5 loads. Notice that each of these resistors have 1K ohm, or 1,000 ohms of resistance each. Separating this parallel circuit out from the others, we could use our resistance configured multimeter to measure the total resistance of this parallel circuit. Under this measurement, the meter would display 500 ohms, even though each of the resistors have 1,000 ohms each. Refreshing our memory referring to parallel electrical circuits, the formula of 1 divided by 1 divided by R1 plus 1 divided by R2 is used to determine this parallel circuit's total resistance. Plugging these values into the equation of 1,000 ohms of R1 and 1,000 ohms of R5, we calculate the total resistance to be 500 ohms. We can now understand that this 500 ohms of total resistance of this parallel circuit is now in series with the other networked loads. Doing the same process with the parallel circuit on the right, made up of the R3 and R6 resistors, we can calculate its total resistance values. If we isolate this parallel circuit and measure with a resistance configured multimeter, with the power removed, of course, 500 ohms of resistance will be displayed. Like the previous steps with R1 and R5, we find the total resistance of this parallel circuit by the formula shown. 1 divided by 1 divided by R3 plus 1 divided by R6 will calculate to be 500 ohms of total resistance of this parallel circuit. Notice in this graphic the R1 and R5 resistors in parallel providing 500 ohms. The R2 resistor provides 1,000. The R3 and R6 resistors provide a 500 ohm resistance, and the R4 resistor provides 1,000 ohms. When placed into a series pattern, and when the resistance configured multimeter are used, 3,000 ohms of resistance is total. We can identify the source of the power to be 9 volts DC and apply to the circuit. Using Ohm's law, we can determine circuit amperage by dividing the known applied voltage by the known total resistance. Entering these values into the Ohm's law formula for amperage, we calculate 0.003 amps. If this 0.003 amps is coming from the battery, this same value of 0.003 amps is returning back to the battery. We can now use Ohm's law in order to calculate the voltage drops across the resistor loads. The formula that we will use is going to be VD, which is the voltage drop, is equal to the amps multiplied times the value of the resistance. To find the voltage drop across this parallel circuit, 0.003 amps is multiplied by the total resistance of this parallel circuit, having 500 ohms. Entering these values into this equation, we calculate the voltage drop across the components to be 1.5 volts DC. Applying the same equation to the R2 resistor, 0.003 amps multiplied times the 1,000 ohm value of the resistor number 2 equals 3.0 volts DC dropped across this load. The same process used in calculating the voltage drop across the R1 and R5 resistors can be used to calculate the voltage drop across the R3 and R6 resistors. 0.003 amps multiplied times the 500 ohms of total resistance of this parallel circuit equals 1.5 volts DC dropped across it. 0.003 amps multiplied times the 1,000 ohm resistance value of the R4 load equals 3.0 volts DC dropped across it. We have just completed solving this networked circuit's voltage drops across each of the loads. Our final steps involves the amperage through the network circuits. We have already calculated our circuit to have 0.003 amps passing through it. Starting with the first parallel circuit on the left, we identify 0.003 amps entering into it. We calculated and perhaps measured the 1.5 volts DC dropped across this parallel circuit. Referencing the Ohm's law formula for determining amperage, we understand that amperage is equal to the volts divided by the resistance. Utilizing this formula in this case, the 1.5 volts DC dropped across this particular load is divided by the resistance value of the R1 load of 1,000 ohms equals a current passing through it of 0.0015 amps. If an amperage meter is placed in series with the R1 resistor, this 0.0015 amps will be displayed. Notice at the right, the same calculation is used to determine the amperage of the R5 load, and then the same value of 0.0015 amps. We can use the same Ohm's law formula to find amperages used by the 1000 ohm R2 resistor. The voltage drop of 3 volts DC divided by the R2 resistance of 1000 ohms equals 0.003 amps passing through it. Performing the same calculation as done in the previous parallel circuit to the R3 and R6 resistors, we calculate the 0.0015 amps passing through the R3 and the R6 paralleled resistors. The R4 resistor calculates to have 0.003 amps passing through it. In summary, networked circuits can be simplified and analyzed using our previous knowledge of Ohm's law applied to series and parallel circuits. We can also verify our calculations by utilizing multimeters in different configurations of voltage, amperage, and resistance.